Welcome back, class. Today we're going to continue our discussion on Lewis theory, and we're going to start our focus on Lewis theory and covalent bonding. So just to kind of refresh us, remember that in covalent bonding we have the sharing of electrons, right? Now, when we share electrons in a covalent bond, it's important to understand that the electrons, the shared electrons, count toward both of the atom's octet, right? So it is literally shared, right? It gets each of the atoms involved in the bond one step closer to satisfying that octet. Now, if we look at the Lewis structure of water, right? And if we remind ourselves that, this is the Lewis symbol for hydrogen. This is the Lewis symbol for oxygen. Now, notice I've gone to the liberty of putting the pairs on opposite sides just to make it easier to see here. Now, again, it's not really crucial which side the pairs are on and which side the single one's on, right? It's that we have two sides that are paired up, two sides that are not. And we can sort of imagine these two things coming together to form a sharing here and a sharing here. Now, by looking at the Lewis symbols, right, we could predict that oxygen would like to share twice, right? Would like to make two bonds, if you will, because it needs two more electrons to get to an octet, right? It has 6, it needs to get to 8, and so sharing twice is going to be, right, what it needs to do. And so getting back to sort of the thing we talked about at the opening, right, there's a reason why it doesn't only share once, right? Why OH, why a neutral OH, or 3 times, a H3O, right? Because there's no desire now to share. Once you share twice, oxygen is satisfied. So this is why H2O is the stable form of a neutral combination between hydrogen and oxygen. So we can get to this. Now, we have some nomenclature here. The shared electrons that go into forming our bonds are called bonding pairs in Lewis structures. And the ones that are not involved in bonding, but are part of satisfying the octet of an atom in a Lewis structure, are what we call a lone pair, sometimes referred to as a non-bonding pair. So we'll use that terminology a lot when we start talking about Lewis structures. So when these two atoms share one pair of electrons, right, we call that a single covalent bond. And of course, it involves 2 electrons. Right? Every sharing of electrons, right, we think about it as a 2-electron sharing. So we can see here, if we sort of draw the circles, right, that by making this sharing, that oxygen's octet, shown here in red, right, has 8 electrons, right? 2 that are part of, 4 that are from the 2 lone pairs, and 4 that are part of this sharing, are part of the bonds. Now again, notice these two that are shared, right, also, of course, count for the hydrogen. So again, our bonding electrons are doing double duty, right? They fulfill or count toward the octet of both of our bonding atoms. And by doing this, we see that each hydrogen has satisfied its desire for a duet, right? Remember, hydrogen only wants 2 electrons. It can't get to an octet. Now, as we see here, right, an oxygen atom or any atom might make more than one bond in order to satisfy its octet, right? It can make multiple single bonds to multiple different atoms to satisfy that octet, right? Oxygen here wants to share twice. It could choose to do that with 2 different atoms. Now, it could also choose to do it with the same atom, right? We have something in covalent bonding where an electrons or an atom can share multiple electrons with the same atom. So let's look at that a little bit. So for example, when oxygen comes together to form the O2 molecule, right, the stable form of oxygen, it doesn't share twice with two different atoms like it does in water, but it shares twice with the same atom. So it shares twice with the same oxygen atom, forming what we call a double covalent bond. Right? And this involves the total sharing of 4 electrons. Now, it's not exactly the same as 2 single bonds, right? It is a different bond, and we'll talk more about that as we get into bonding, right? It's not 2 separate bonds. We think of it as a one, what we call double bond. And the way we symbolize that is with a double line between the 2 atoms. Of course, this is all oxygen needs to do, right? We formed this double bond, right? That satisfies the octet. We have a stable O2, right? Now, but other atoms that might have to do this might need to share even more, right? So we can also, of course, share 6 electrons between 2 atoms. So in other words, an atom can equivalent to bonding 3 times with the same atom in order to satisfy the octet. Right? So we see this commonly in something like N2. Nitrogen will tend to do this more than other atoms because if you look at the Lewis structure of nitrogen, or the Lewis symbol for nitrogen, right, it has 5 valence electrons, right? It needs to share 3 times. And it will choose to do this often with 3 different atoms. It could do it twice with one atom, once with another atom, or it could do it 3 times with another atom and form what's called a triple covalent bond. It involves, of course, the sharing of 6 electrons. Now, we will talk more about these in terms of when we see them, how to know if we have them in our structures when we start drawing bigger Lewis structures. Now, we can't share any more than 6, right? A triple bond is the highest that we see, right? We can have single, we can have double, we can have triple, with single being by far the most common, then double, and triple bonds are not terribly common in structures. Now, all this is nice, but it seems to imply that when we have this sharing, that sharing is what we call equal, or what we might refer to as equal, right? This is how it looks, right? We just have a line. This atom is contributing 1 electron. This atom is contributing another one. They're shared, and we go about our business. But, of course, it's not that simple, right? A lot of bonds would have what we call non-equal sharing, where one of the atoms has a stronger desire for the electrons than another one. Now, we looked at water earlier, and water is an example of a structure that has this non-equal sharing between hydrogen and oxygen. So we're going to spend the next little bit talking about how we can explain this non-equal sharing. Now, the property that we focus on to try to explain this is called electronegativity. So an electronegativity of an atom is its ability to attract bonding electrons to itself. So when an atom forms a bond, how strongly can it attract those electrons to itself? This is called its electronegativity. The higher the electronegativity, the stronger that it can pull those electrons or attract those electrons to itself. So if we think about this trend, this is another example of a periodic trend. We talked about things like ionization energy and size, right? Electronegativity is another example. So a couple of things to point out, and then we'll look at the table, is that the highest electronegativity atom is fluorine. Right? It is the most electronegativity atom. Whereas francium, down in the lower left-hand side, is the least electronegative atom. Noble gases are not given values, right? Because They really have no desire to pull electrons to anywhere. They're stable. And as when we look at the table, we'll see that it is sort of the opposite of size. So in other words, small atoms will tend to have high electronegativities. Big atoms will tend to have smaller electronegativities. And the bigger the difference between the electronegativities in the two atoms that are trying to bond, we say the bond is more polar. So we're going to go about the idea now of determining whether a bond is what we call polar. Okay, so let's look at this. So here is our electronegativity table. So we have this superimposed on a periodic table, and we can see up here, we see fluorine, right? The highest electronegativity element. Now, the electronegativity scale is on a 4, right? 4 being the highest. Fluorine has a value of 4. Every other atom is lower, and we can see the trends. So we can see, as we saw, the trends are as you move to the right. And remember, atoms get smaller as you move to the right across the periodic table. The electronegativity gets higher, right? And we can see that, right? As you look at these nonmetals, we see that carbon is 2.5, 3, 3.5, 4, right? We get a ever increasing. As we go up a column, the electronegativity gets higher. So we can see that if you start like iodine, again, 2.5, and bromine's a little higher, chlorine's a little higher, then fluorine is a lot higher. And we can see this general trend of increasing electronegativity as you go up a column or decreasing as you go down. Now, if we put these two together, right, we see the lowest electronegativity down here with francium, and we have this sort of diagonal trend as we get increasing electronegativities as we go up and to the right. Now, of course, since we're going to be focusing on covalent bonding, we are mostly going to be concerned with the atoms right here, right, and how their electronegativities vary. And so we can see the trends, and again, remember, it's if you're thinking about other trends, right, it's just the opposite of size, right? Notice the smaller atoms are also up here, right? Size gets smaller as you go to the right, gets smaller as you go up. Bigger atoms as you go down, and off to the left, the electronegativity goes down. Okay. So now that we have our electronegativity, and we know how to sort of what that entails, we can start to say, what's a polar bond? What's a nonpolar bond? So when we have unlike atoms bonding, of course, if it's the same atom, right, they're going to be equal sharing because the electronegativities are exactly the same. But if we bond unlike atoms, we will often get unequal sharing. The one atom pulls the electrons closer to its side. Now, we call this a larger electron density. So the end of the bond that has the larger electron density, meaning the electrons are closer to the other, we give that a negative sign, right? So we're going to set up a negative and a positive end of the bond, right? Where the negative end is going to be on the side where the electrons are drawn more heavily to. The positive end is going to be on the side where the electrons are less drawn to. If this sharing is unequal enough, and we'll talk about what those values have to be, then we have what's called a polar covalent bond. And again, larger electron density gets called a partial negative, and the way we abbreviate that is with a little what we call a delta, it's a lowercase delta, negative. And the one that's more electron efficient or has the lower electronegativity gets what we call a partial positive charge, which we label a delta positive. Now, the reason we use this symbolism is to distinguish it from an actual charge. So these are not ions, right? We are not transferring electrons. We're not forming actual ions. We just have a difference in electron density. So we have a negative side of the bond and a positive side of the bond. So if we check out the table, right, what makes a polar bond versus a nonpolar bond? Well, the simplest way to approach this is just to look at the electronegativity difference. So if we look at our table, if we have a small difference, so between 0 and 0.4, we have a simple covalent bond, or what you might refer to as a nonpolar covalent bond. So you might see this in where the atoms are the same, or in certain things like for example, we're going to look at, a CH bond, and most times a CH bond where the electronegativity difference is 0.4, in a lot of circles that's considered a nonpolar bond, right? And so there's not enough separation to really make it behave like a polar bond. If we have a separation bigger than that, so I know it's confusing to say 0.4 here, but really what we're looking at is 0.5 and above. Now, this book makes the cutoff at 2, right? This is not a uniform number. Other books will make the cutoff at 1.9. Other books will even talk about it as low as 1.6, right? So this is sort of at the higher end, right? There's a more complicated, right? It's more complicated than just looking at the simple electronegativity difference. But if you're within this sort of continuum, this is where you have a polar covalent bond. Now, if you're above this, now again, this book's going to call that above 2, but you'll see examples where it's not exactly where it's below 2. You transition into an ionic bonding. So the idea is that once this electronegativity gets too high, the difference, in a lot of cases, you can no longer share electrons. They simply get transferred. It's like tug of war, right? The strengths of the two sides becomes bigger and bigger and bigger difference. At some point, the electrons are just ripped away by the atom that has a stronger desire for them. Now, again, this is more seen on a continuum, right? So we have this idea of equal sharing, which the book throws in this pure. I'm not going to use this pure nonpolar. We're just going to call it nonpolar. And this would, for example, be something like, say, a Cl-Cl, right? Or where it's the same. Now, as you go onto this fairly large continuum of difference in electronegativity, you might see something like ClH, right? HCl, right? This has an electronegativity difference, right? And we could calculate that exact electronegativity difference by looking back at our table. And so we would see that if we look at Cl, it has an electronegativity of 3, H has 2.1. So our delta E here, delta electronegativity is 0.9, right? It falls on this continuum. Right? You're going to get a nice polar bond where the chlorine is going to be more strongly attracted with an electronegativity of 3.0. The hydrogen with a 2.1 is going to not pull them as strongly, and so it's going to be the positive side of the bond. Now, you get something like NaCl, all right, where you get a difference of about 1.9. Then you're in that area where you're not going to see, so you have 0.9 and 3. So actually you get a difference of 2.1 there. So you get well into that ionic part of the spectrum. So this is the simplest way, and the one that frankly we'll use the most often in order to determine whether a bond is simple. And I'm just going to expect you to use these basic cutoffs, right? If I'm just asking you to determine the polarity of a bond. Now, as I said, the picture's a little bit more complex, so we can look at that a little bit. Now, there's something called the dipole moment, which is abbreviated by this mu symbol here, and it is another way to measure bond polarity. Right? And so this is the sort of measures the difference between the positive and the negative ends of the bond. It is related to the size of the partial charges, so how positive, how negative, and the distance between them. And so if we think about the distance between the atoms, so how long the bond is, and the size of the charge. So we could do sort of a simplified version of calculating a dipole moment for, now this is going to work, this particular, right, if the particles have equal charge. So the book goes through this example where you sort of look at the dipole moment, or the ideal dipole moment in an ionic bond where you get a proton and electron, right? So they're going to have the same charge but opposite, and you plug in a sort of a length for that bond. And the book uses 130 picometers. That's kind of a, I want to say a normal length covalent bond, a little bit shorter, but it's a nice good number. And ultimately what they get is they get a value of 6.2 for the dipole moment. And this is used as sort of an ideal ionic bond, right? Where we get complete transfer of the electron from one to the other. So we'll see how this is used in a second. Now, if we look at a table of dipole moments, you can see, right, if you have two bonds that are the same, of course, they're not going to have any dipole moment. If you get things that have, a reasonable difference in electronegativity, right, you see a dipole moment. Still not very big, right? Now, this is where I want to sort of see now we're right on the cusp, right? Your dipole moment is not all that big. We take an example of lithium fluoride, clearly an ionic compound with a metal and a non-metal. Your delta electronegativity is very large, right? Your dipole moment, very large, right? So they do track well in terms of the predictions of dipole moment and electronegativity in predicting polar bonds. Now, where can we see some confusion? Well, if we look at, and we'll remember the 6.2 value here in a second, we look at another measure, right? And this is something called percent ionic character. And based on this kind of idea, if you're more than 50% ionic, then you're considered an ionic compound, right? So if you have more than 50% ionic character, then you're considered an ionic compound. So it's this continuum, right? If you're below 50%, you still would have covalent bonding. If you're above 50%, you start to have, you're going to have ionic bonding. And so, again, if it's more than 50% transferred, it's transferred, right? That's the idea. Now, how do we calculate this? Well, we calculate this by taking, so the percent ionic character equals, let me do this in a little bit easier color to see. We look at the observed dipole moment, right, in our bond, whatever that happens to be, over sort of the ideal bond. And so this, in the book, they use this ideal being where the electron is completely transferred. So we use this value of 6.2 that was estimated, in the book for that sort of ideal transfer, times 100. And you generate a table that might look something like this, where if you get above 50%, you're going to be considered ionic. If you get below 50%, you're going to be considered a covalent bond. And you can see, right? We get most covalent bonds are way down here in the lower left-hand side where you have very low ionic character, under 25%. Now, this is plotted against delta electronegativity. And again, most of these are going to have difference in electronegativity below 1, right? So 1 and below. Right? That's for the bulk. Now, of course, you are going to see some some covalent compounds like HF that have really high differences in electronegativity, right? So remember, H is 4, fluorine is 4, H is 2.1. So you're getting that 1.9. You're very much on the cusp. But you're below 50%. So it falls in the covalent. Now, the ones that get even confused, start to confuse people, is that you'll see ionic compounds that fall in this difference in electronegativity range below 2. So simply based on difference in electronegativity, you would calculate these to be covalent, right? So if I look at, for example, lithium iodide, right? You get iodide is, let me see, I think 2.5, and lithium is 1. So you get a 1.5 difference. On the scale of difference electronegativity, that's clearly covalent. But in terms of percent ionic character, they're above 50%. So they're going to exhibit ionic bonding, right? Because their observed dipole is going to be, higher than what's necessary to get 50. So, based on this, right, you need this to be greater than or equal to 3.1. Right? And that's going to give you your 50% or above. So if you have a measured dipole above 3.1, right, you're going to fall into that more than 50% ionic. And you're going to start getting to, you're going to be an ionic bond, even if your electronegativity difference doesn't meet that, quote, cutoff. So those cutoffs are a little bit, vague, if you will. Now, again, I'm not going to ask you to get into all of this in terms of when we're working with things, because we're going to be working mostly with things that are going to fall well within the range where there's really no question. But if you're looking at the data, you clearly could easily see that, there's going to be ionic compounds that have difference in electronegativity that would, on our scale, would say they should be polar covalent bonds, not ionic bonds, but they have a dipole moment that is higher, typically higher than 3, at least, so they're going to follow into that ionic character. So that's sort of the big picture. Now, why do we see that? Well, think about, what's making up the dipole moment, right? If you look at some of these, right, they have they're big atoms, right? So iodine, very big atom. Right? If you look at, potassium, right? Right? Cesium, right? These are also pretty big atoms, right? So you got big atoms here. At least one big atom involved in some of these, right? That's going to make the bond longer, right? Now remember, if we're using that Q times length, right? If the length gets longer, the dipole moment gets bigger. Right? Also, if you get, bigger charges, right, on these structures, you can start to get into these bigger ones. So bigger atoms will tend to, fall over here. All right. So enough about this. We are going to use this idea of polar bonds when we start getting into drawing Lewis structure. Again, mainly the idea of difference in electronegativity to predict whether bonds are polar or nonpolar. So next time when we come back, we're going to get into drawing Lewis structures for molecules.